first thing here. Let me take this, to me, in a way, the most simple possible example, and to me it's pretty simple, which gives us some problems with the theory and the methods and the tools that I have taught you in this course so far, and what people are typically taught in introductory statistics classes. There is a limit to what we can teach you in a 5-point course, right? And today, actually, we're gonna blow away these limits a little bit. That's what I sort of warned you about, but let's see how it goes. Maybe a little silly, some of it. Now we produce some plates here. We're not doing it very well. We are doing some randomly produced plates. The length of the plates in meters, on average 2 meters, but they're not the same each time. There is a standard deviation of 1 centimeter. So plus minus 2 centimeters. It comes on the length. It's not a particularly precise guy we have standing and making the cuts there. What about the width of these plates? They are also, they're on average 3 meters, but with there's an even less nice guy on the cutting. He has a standard deviation of 2 centimeters. So it's not, it has a sort of spreads between plus minus 4 centimeters or so, this 3 meter cut that he's doing. So what we are interested in is not the length and the width, it's the area. That's what is irrelevant. When we, the area expresses how much material we use, it will express the weight, it will express the cost. It's the area that we're interested in. Now the little thing about the area, we learned that pretty early in school, that the area is the length times the width. The length is random, the width is random, so the area is also random, right? And the area is a random variable which is a function of 2 other random variables, right? And the tricky part is, this is a nonlinear function, right? It's x times y. That's a nonlinear function. And that makes we haven't learned anything about nonlinear functions of random variables in this course so far. And it's complicated. You need to take some more classes if you want to know the theory and tools to actually handle that. So just because I want to compute the area, I'm lost. So I've given you tools and a lot of whole course, and when you go out in the real world and someone tells you to do statistics on the area, I studied engineering 5 years, no one told me how to do statistics on the area. Well, now I'll tell you. There could be different questions posed here, classical questions. What is the mean area of such plates? You would probably think you know, and you do. Don't worry about that. Common sense rules many times. However, more complicated. What is really the variability and or the standard deviation on the area? How much can the area differ from time to time? I haven't taught you how to find that one. Or more things, probability conclusion, probability questions. How often are such plates off the target area, which is the 6 square meter thing? How often will it be more off the target than 0.1 square meter, for instance? That's a probability question. How often does that happen when I produce plates? And I say generally the question that if I can answer that, I could answer all the other ones, actually, if I was clever enough to know how. What is really the probability distribution? Can I find the density or the distribution function for the A variable? I know it for the x, I know it for the y, but what is it for the A? A is a nonlinear function of x and y. Such transformation rules exist, theoretical rules. You have to take the probability class 02405 to learn about those and to learn how to use them. It's a pretty mathematical course. It's a really nice course with a brilliant teacher, Bo Friis Nielsen. I can recommend it at any time. However, you need to take a full 5 points class with a lot of math to get there. If you love math, perfect. If you don't, listen in. Or if you're lazy, listen in. Or just a little bit curious, listen in. Here's the solution. I'm sorry, Bo, I don't care about your class. No, that's silly. I like the class. But here is just a way to do it without taking a full 5 points class. I just let the computer find out for me. It's not very difficult. It's very easy. Now I just set the seed. As I said, I don't have to, but if you want to reproduce my results, you should use exactly the same seed value. Then I set the number of simulations that we do. It should be a large number. I just arbitrarily chose 10,000 because my computer didn't get tired of that. Probably it wouldn't get tired of 100 or a million either. You can just try to see when your computer starts using more than a millisecond. You can skip the zeros. Then I simulate 10,000 lengths and 10,000 widths independently from each other, right? 10,000 times I get a random normal number with a mean of 2 and a standard deviation of 0.1. And then I just look at the numbers. Question. We'll see. How does the seed value influence the results? Let's have a look at that and talk of that in a sec. Very good question. Important question. I just look at the results and say, what is the mean of the area? I just compute. I get 10,000 area values out, right? So I can just look at those 10,000 area values. And if I want, I could get 1 million by putting k to 1 million. Here is the probability distribution. Because I have 1 million outcomes or 10,000 outcomes of the area, let me just look at those empirically. That tells me what is the probability distribution of what's going on. And I can extract whatever question I have about what's going on from these numbers, right, in the computer. I can compute the mean. I can compute the standard deviation. Seems to be 0.05. I can compute, and here's a little R thing. If I wanted to find out how often is my area more away from 6 than 0.1 square meter, right? That's the question I put on the slide. I use the logical operator. I use the absolute function, saying, here's the difference between A and 6 that produces 10,000 differences. I take the absolute value, that is, I make them positive, all of them. By using the logical operator, I produce a 10,000 vector of trues and false. And in R, by default, trues are 1s and falses are 0s. So I can just compute on this vector of trues and false as if it was 0 and 1s, because that's how it is also interpreted if you can use it like that. So by taking the mean of those 10,000 0 and 1s, I get the proportion of 1s, right? I simply count the number of 1s divided by 10,000. That's another way to say it. Number of 1s divided by 10,000, that is 4.4%. So that's the probability of getting this result. Then we had this, let me see. Yeah, then we had this very good question about, and let me jump into R. How does setting the seed influence the result? We could also have asked similarly, same kind of question. Let me go down to, we can just do like that, on the mean and standard deviation. Let me do it once now. Let me set the seed like before, like that. I do it once now, right? I get the result 5.99 and this 0.0495 as the standard deviation. You point your finger at an important thing because this is probably not 100% correct, this thing, because it's based on 10,000 simulations, right? Before answering your question or the same question, I could also have asked, what if I do it again? I mean, even though not in a way setting the seed again, but just doing it again. Will I get the same result? Yes and no. Practically, yes, but exactly, no. I'm struggling a bit with the mouse here on this one. Oh, come on. There we go. The means are not exactly the same, and the standard deviations are not exactly the same. They're similar, but not exactly the same. So we don't get the same result, and that's exactly the same answer to your question. What if I set the seed at a different place? It's like doing it again, because when I did it again, the seed had changed anyway, or the position of the algorithm moved. So like doing it again is like changing the seed, right? So whenever we do it again, it's like having a new seed. So of course, this is a core thing that we should think about. Is it good enough? Is it the right result? And hey, how should we investigate that? If we're in doubt whether this is the right result, shouldn't I just try again and check? That's the same statistical idea as I've taught you previous. Thank you. Or I have to do my cut and pasting in a more relevant way. Yes, thank you. Don't ever look away when you do something. Here. What is happening now? Oh yeah, good. It actually changes. I just thought it didn't change. It changes, but it seems like 0.05 must be pretty close to the true answer, right? So I'm just saying, and this is where I'm not going to formalize this now, because we only have one day to talk about this, so that's where I can. This investigation of whether it's good enough can, of course, be formalized. So you can try to increase n, but I'm just doing it a bit ad hoc here. Let's see if it gives me more or less the same result. If it does, yes, it's good enough, right? That's as far as I'll take it. But that can be formalized, of course. You could put it into a procedure. Let me check the statistical noise, the simulation error, by the same statistical procedures that I taught you before the fall break, actually. But we're not gonna do that formally now. I'm just going to say, you just have to do k large enough, and then you just double check that it seems to be precise enough. That's as far as we have the time to do it here. Hope you get the feeling that you can go and check. It's not because I'm saying you shouldn't or couldn't do it, but we don't spend the time on the formality. Thank you for that question. Then we jump to the third part of the first lecture, where we again take some statistical issues, statistical